Hello and welcome to Mr. Linford's math course. In this discussion, we're going to be introducing the topic of the irrational number e. We're going to talk about what the number e, or the constant e, represents, and then we're going to get into a specific type of logarithmic function. It's what's called the natural logarithmic function. Now, the number e is an irrational number. It is a value or a constant, kind of like pi. It's a number that goes on forever and ever as a decimal approximation, and it never repeats a pattern. So e, very similar to pi, it's a non-terminating decimal as we approximate it, and it never has a repeating pattern to it. Now, unlike pi, e doesn't really come from anything geometric. Meaning pi is the ratio between the circumference and the diameter of a circle. Now, and then we also have things like the square roots, square root 2, square root 3, square root 4. Those are all really based around triangles and the hypotenuse of different triangles. So those are very geometric forms of irrational numbers. E is an irrational number that really comes about by studying patterns and studying the patterns of different growths. E is defined a couple different ways. There are multiple ways to go about thinking about E or how to approximate it. The way our textbook uses the definition is that E is the constant value produced by the function f of x equaling 1 plus 1 over x in that whole quantity to the x power. So before I finish this definition, I want to reread what we have here. E, the constant e, is a constant value produced by the function f of x equaling 1 over x to the x power when x approaches infinity. By this, I mean, as you plug bigger and bigger numbers in for x, you will get out of a number that gets closer and closer to e. So as you plug things in for x like 100, a million, a billion, a trillion, a quintillion, whatever, the more you plug in bigger and bigger numbers for e, your output will get you closer and closer to the number e. Did I say that right? Let me say that again. The bigger the numbers that you plug in for x, the closer your answer gets to approximating e. So if I were to plug in, say for example, 1 plus 1 over, let's pick a really big number, 10 to the 100th power, and that whole quantity to the 100th power, that's going to be close to the number e. If I plugged in 1 plus 1 over 10 to the, let's say, 200th power, and that whole quantity is to the 200th power, that's going to be even closer to e, right? Even closer. The idea here is, as you continue to grow, as x continues to grow, as it continues to increase, what does your output look like it's producing? Now, and you can try this for yourself. Make a table and start plugging in big numbers for x. Plug in 10, plug in 100, 1,000, 10,000, a million, a billion, a trillion. You got a calculator. You can go ahead and do that. Give it a try. See what you end up with. You'll find that all of the values get you closer and closer to this constant term e. Now, I keep referencing what e is, but I never actually tell you what the decimals approach. So let me go ahead and write that down. If we were to take bigger and bigger numbers for x, we would get incredibly close to this decimal value. E is approximately 2.71828 and I'm going to round off here 5. And it keeps going. It keeps going on and on and on. Okay? Those are just a few of the many digits that are that belong to E, of the infinitely many that belong to E. Now, we are going to work with this definition because it's fairly simple, but there's other definitions out there too. Some of you might know about summation notation. We could say that E is actually equal to the sum from n starting at 0 and going off to infinity for 1 over n factorial. That's basically saying take 1 over 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3 plus etc. And you just keep repeating that pattern. So that's when we have summation notation. That's another definition for E. This is what's called an infinite series, and an infinite series definition. There's others out there as well. There's definitions, I think, that they talk in the popular number file series. They actually talk about a definition Euler worked with for continued fractions. But this is I would say, the most easy to work with definition. It's the values that you get out for this function as you approach infinity. As x keeps getting bigger, what does the function produce? Okay? Now, the history, I'm not going to go too much into this. I think I'd save that for another video. But E is a really fascinating number. People oftentimes would say in math class, oh, what's the coolest number ever? And people might say pi. And pi is a very cool number. Other times people might just pick a random number, right? E has an amazing history to it and an even more amazing amount of applications. We're going to just barely graze the surface in this class of all of the many applications to the number E and its usefulness. But E started out being discovered by, it was the Bernoulli brother, Jacob, and I think, I'm just going to spell it like normal Jacob, but I think he had a K in his name. Jacob Bernoulli. Jacob Bernoulli, one of the members of the Bernoulli family. The Bernoulli family were a very Renaissance family of mathematicians, physicists, engineers, artists. And he was one of the Bernoulli brothers, I believe. And he actually discovered this. He's a Swiss mathematician, physicist, and polymath, really, that discovered this in a very unique way. Unlike the ancient Greeks who discovered irrational numbers by studying geometry and shapes, it seems almost like fate that Bernoulli was discovering this by studying something called compound interest. Compound interest is how money is accumulated by gaining interest. So he discovered this. It was discovered by Jacob Bernoulli as he studied compound interest. Compound interest is basically how many times, so you earn interest when you have money in a bank account. Now, there's simple interest, meaning you earn the same amount of money every time, right? Like if you invest $100, so if I invest $100 and they're going to give me a rate of 10% every year, that means I would get $10 after the first year in my bank account. Well, simple interest says This is how much you're sticking with as your interest payment every year. Every year, they just keep giving you $10. $10 the first year, the second year, the third year, etc., or however often they give you your interest. Now, compound interest works a little differently. Compound interest would say, okay, you invest $100 in the bank, and let's say the rate is 10% interest. They're going to give you 10% of whatever you put in the bank. Okay. And let's say they compounded it once a year. What I mean by that is, okay, at the end of the first year, they give you 10% of $100. So you now have $110. What the bank means by compounding is they're now going to take 10% of that new quantity. So if they were to take another 10% of that, so take 110 times 0.10, and you're going to get $11. So now you have $11 plus 110, so you now have $121 in your bank, as opposed to 120. Compound interest lets you grow your money much quicker, and this is generally what happens with a bank. What Bernoulli was doing is he was looking at what happened to money, to the amount of money you earned, your interest that you've earned, as banks or whatever financial institution compounds your interest more and more. Now, maybe your bank compounds what gives you your interest once a year. Maybe they compound it twice a year. Maybe quarterly, 4 times a year. Maybe they do it monthly, 12 times a year. And what Bernoulli was doing is he was looking to see what happens the more times they compound it. And he started discovering this constant that would pop up. Now, I don't want to go too much into Bernoulli's work, but I'm going to leave that for a Numberphile video. There's a really awesome YouTube channel called Numberphile that's out, and it has a sister channel as well called Computerphile. It's a fantastic channel, basically, that talks about math. The documentary producer to the show and cameraman, Brady, started this project where he would interview PhD students, doctoral students. He'd interview math professors and some really big names in the math community about different, unique, and cool concepts in mathematics. And they actually have a really awesome video about the number E. So I'll link a video to that down in the description and on the course website for you to take a look at. But some interesting things to know. It was discovered by Jacob Bernoulli when he was studying compound interest. So it's kind of difficult to really get your head initially around the number E because it's not something you can really picture geometrically. It's more so something that occurs as values change. Now, the number E, of course, being discovered by Bernoulli, it was really perfected, and I'm going to use that term, perfected, by the mathematician and the great Leonard, and I want to spell his name correct here, Leonhard, and then Euler, Euler, Leonhard Euler. The great mathematician, Leonhard Euler, who is considered one of the greatest mathematicians of all time, is a Swiss mathematician, physicist, polymath of all kinds, did incredible work in elements of physics, whether it be optics and dynamics, stuff that Newton was looking into. He also did an incredible amount in mathematics as well. Topology, number theory, you name it. He was involved in it. Now, Euler is famous for, one, giving E its name. So Euler here actually named the number E. He gave it that symbol. Some people say, did he name it after himself? It's called now Euler's constant. E actually is referred to as Euler's constant. Yes, Bernoulli discovered it, but the majority of work that was done with the number E was done by Euler. Bernoulli actually taught Euler, well, I should say he taught, I believe the story is Bernoulli taught Euler's father, who then taught him, and in particular shared with him the work with the number E. Now, Bernoulli was also taught by, Euler was also taught by the Bernoullis as well. His doctoral advisor was a Bernoulli. Johann, I believe it was his name. I tell you, this Bernoulli family was rather gigantic in all that they contributed. So Euler was very well knowledgeable about this value E. However, he would go on to do the majority of work with it. And in fact, Euler himself would develop his own equation for the number E. So Euler did the majority of work with E. He used it quite a lot, and in particular for dealing with complex numbers. Euler really did quite a lot to advance our understanding of complex numbers and values related to I through his study of E and his application with that. Now, if you go on to study mathematics or physics, even if you go on to study engineering at a rather high level, in particular electrical engineering, you'll come across E quite a lot. The value E, in fact, is used constantly all over the place for things such as cell phones. In fact, wireless communication really relies a lot with the number E. Electrical currents and our study of electrical currents, which do in fact rely quite a lot on complex numbers, are going to require us to also understand the value E for switching between real and complex values. There's all different types of applications to this very powerful number. Unfortunately, we just barely get to graze the surface on it, but I encourage you, look into this number, look into its unique history, and feel free to ask me any questions that you have about it, or if you want to know more applications, I'll help point you in the right direction. Now, with all of this said, let's get into some of the actual mathematics that we can use with this number. One of the big areas in which we are going to apply E is what's called the natural logarithmic function. Now, the natural logarithmic function is in fact going to be a function. So we're going to start there with f of x. And it's going to be a logarithmic function. So before, when we were studying logarithmic functions, we would say something like log base b of x. And b was supposed to be a real number. And we looked to see what would happen as we changed b around, and we saw those different curved shapes. Maybe they would be growth or decay. Now, what we have for the natural logarithm is where we have a very specific b value. Rather than saying we have log base b of x, I'm going to change b, and I'm going to set it to be the constant e. When the constant e is your base value of a logarithm, you have the natural logarithm. So now, we sometimes don't always write things as log base e. We actually change the symbols to be ln of x. Now, it's important to know this distinction here between having log base e and ln of x. They mean the same thing. It's just notation-wise, it's much more common for us to write the natural logarithm as ln. Now, why ln? I don't remember exactly. I think it's a phrasing, probably in another language like Latin. But it always is going to refer to as the natural logarithm. Now, in your calculator, this is the general symbol for when you want to do log base e. They generally don't have a button for log base e. Actually, your calculator, now you could in most scientific or most graphing calculators manipulate that, but in scientific calculators, you're really just going to see the natural log of x, or you're going to see log of x. Sometimes, in most cases, I'd say with scientific calculators, you can't always change the base value. And they have it predetermined, set to be 10. Now, that's just for most calculator usage, especially in the Texas Instrument calculators. There is going to be the button ln on your calculator. When I refer to the natural logarithm, I am going to be using the ln notation, and I'm going to be indicating that you press that button on the calculator, okay? We're not really going to want to work with this. You could, but you want to make sure that you're comfortable with this notation. Now, we do have some properties with the natural logarithm function. For example, start by letting x and y be positive real numbers. And also, p here is just a real number. It can be any real number. These 7 properties hold true. These properties are the exact same properties that we had with the regular logarithmic functions. We sometimes call those the common logarithmic functions, okay? If I wanted to prove these, I already did. I can just rewrite this natural logarithm to be log base e of 1 equaling 0 and show that e to the 0 power is 1. So I already went through and explained all of these in the general sense, but if you'd like, you can go back through those proofs, but this time changing the base to be an e value specifically and seeing why these work. But all of these properties are just showing us that everything we had before does in fact still work. What I'd like us to do is take a minute to go ahead and try to simplify these 4 expressions using the natural logarithm and the properties that we have for simplifying. So pause the video, take a couple minutes, and let's see how you do. All right, well, hopefully you had some time to work through these 4 problems. What we're doing here is you'll notice that I've converted all of the natural logarithms back into our standard logarithmic notation. You can see that I made all of the logs have the base e. I'm doing this now just so we can see kind of how this is working. But if you were to notice that the natural logarithm of e is basically log base e of e, and you could say to yourself, e to what power gets you e? Well, then obviously the answer is just 1. And we have a property for that. Similarly, we have a property for the natural logarithm of 1. What power of e gets you to 1? Well, that's just 0. Now here, if I rewrote this, I have natural log of e for e to the x plus 1 is, same with log base e. E to what power gets me e to the x plus 1 power? Oh, well, that should be pretty obvious. It's just x plus 1. It's whatever that exponent was. Now the last one, we have a property that tells us that the base and the log and the exponent are just going to cancel out, and you'll be left with x plus 1. So here we should say e to the natural log of x plus 1 should just equal the argument x plus 1. But here's kind of a little explanation of why that works. You'll notice that I first rewrote the natural logarithm to be log base e. And that's just for our sake as we're getting used to this concept. I decided to take this exponential equation and rewrite it into a logarithmic equation. We took log of base e, that's the base, the argument is what we get out, and logarithms always equal the exponent that you're trying to find. So we had this setup, and we can ask ourselves, okay, what's missing here? These two are identical, they're the same thing. So what could this unknown quantity be? X plus 1. So that's just a little explanation of where these rules are coming from and why they are. But really be comfortable just going ahead and applying these processes, these procedures for simplifying down your natural logarithmic expressions, just as you would for a log of any other base. That's really all that I had for us to introduce this concept of the natural logarithm. We'll get into some applications and some work with this a little later on. But right now I just want us to understand what's the natural logarithm, what's the number e, and how can we go about simplifying logarithmic expressions. If you have any questions or would like some more information about things like the number e or the natural logarithm, let me know. My email is klinford, that's KLINFORD, @wccnet.edu. Let me know if you have any questions or comments. And until next time, take care.